Hello, curious minds. Welcome back to ProjectCellence ProDigy, your one-stop destination where mechanical engineering meets project management. I'm Govin, a certified PMP and a mechanical engineering professional with more than 25 years of experience in the power and energy industry. In the previous lesson, we started our series on components of a reciprocating internal combustion engine and covered some of the major engine components. Today, we continue with part B of this series. In this lesson, we will explore some more important engine components like fuel pump, fuel injector, pre-lube oil pump, main lube oil pump, HT and LT water pump. We will understand their construction, functions, and role in the overall working of a reciprocating internal combustion engine. So without any further delay, let's get started with today's lesson. Fuel pump. This is one of the most important parts of the fuel injection system. Its job is to supply fuel from the fuel system to the fuel injector at a very high pressure. The injector then sprays this fuel into the combustion chamber in the form of very fine droplets, and this process is called as atomization. Good atomization helps the fuel mix properly with the compressed air, which results in efficient combustion, better engine performance, lower fuel consumption, and reduced exhaust emissions. Apart from supplying fuel at high pressure, the fuel pump also ensures that the correct quantity of fuel is delivered at the correct time according to the engine load and speed. Over the years, different types of fuel pumps have been developed to improve engine performance and to meet strict emission standards. The most commonly used fuel injection systems are individual jerk type fuel pump, common rail fuel injection system, unit injector or unit pump system, and inline fuel injection pump. Now let us first understand the individual jerk type fuel pump, which is one of the most commonly used fuel injection systems in medium speed diesel engines such as Wärtsilä, MAN, and Daihatsu generator engines. As the name suggests, each engine cylinder has its own individual fuel pump. For example, if an engine has 6 cylinders, it will have 6 separate fuel pumps. Similarly, in 12-cylinder engines, it will have 12 individual fuel pumps. Each fuel pump supplies fuel only to its own cylinder. In this system, the fuel pump and the fuel injector are two separate components. The pump is mounted on the engine block, while the injector is installed in the cylinder head, and both are connected by a high pressure fuel pipe. The fuel pump is mechanically operated by the engine camshaft. A separate cam lobe is provided for each fuel pump. As the camshaft rotates, the cam pushes the fuel pump tappet, which moves the pump plunger upward. And this upward movement compresses the fuel trapped inside the pump barrel. As the pressure rises, the delivery valve opens and the high pressure fuel travels through the high pressure pipe to the injector. The injector opens automatically when the fuel pressure becomes high enough and sprays the fuel into the combustion chamber. Once the required quantity of fuel has been delivered, the pressure inside the pump drops and the injector closes and fuel injection stops. The entire process is completely mechanical and is synchronized with the engine crankshaft through the camshaft. One of the biggest advantages of this individual jerk type fuel pump is that each cylinder has its own independent fuel pump. This means each cylinder can be adjusted individually, which makes the maintenance easier and ensures reliable engine operation. Although most of the modern engines are using electronically controlled fuel injection systems, but this individual jerk type fuel pump has its own importance, and it is still widely used in many marine engines, power plant engines, and industrial generator sets because of its simple construction, high reliability, and long service life. Now let's move to the second type of fuel injection system, which is the common rail fuel injection system, commonly known as CRDI system, common rail direct injection system. This is one of the most advanced and widely used fuel injection system in modern diesel engines. Unlike the individual jerk type fuel pump, where each cylinder has its own separate fuel pump, the common rail system uses one high pressure pump for the entire engine. This single pump compresses the fuel to a very high pressure and delivers it to a common pipe, which is called the common rail. You can think of the common rail as a high pressure fuel reservoir. It stores fuel at a constant high pressure and supplies it to all the injectors whenever required. Each cylinder has its own electronic fuel injector, and all the injectors receive high pressure fuel directly from this common rail. Now you may wonder, if all the injectors are connected to the same rail, how does each injector know when to inject the fuel? This is where the engine control unit or ECU comes into the picture. The ECU is basically the engine's electronic brain. It continuously receives information from various sensors like engine speed, engine load, accelerator position, intake air pressure, coolant temperature, and many other operating parameters. And based on this information, the ECU calculates exactly when fuel should be injected and how much fuel should be injected and for how long the injector should remain open. The ECU then sends an electrical signal to the required injector. The injector opens for just a few milliseconds, which allows the required quantity of high pressure fuel from the common rail to enter the combustion chamber. As soon as the signal stops, the injector closes immediately. The high pressure pump continuously maintains the required pressure inside the common rail, while the ECU controls only the injectors. This allows extremely accurate fuel injection under all operating conditions. Modern common rail systems can also perform multiple injections during a single combustion cycle. For example, a small amount of fuel may be injected before the main injection, which is called the pilot injection, followed by the main injection, and sometimes an additional post injection. These multiple injections help reduce engine noise, improve combustion, increase fuel efficiency, and significantly reduce the exhaust emissions. That is why the common rail fuel injection system is now widely used in modern passenger car, heavy duty trucks, construction equipment, industrial engines, and many modern diesel generator sets. Now let's move to the third type of fuel injection system, which is the unit injector and unit pump system. In this system, the fuel pump and the fuel injector are combined into a single compact unit. Each engine cylinder has one unit injector, which is mounted directly in the cylinder head. The pump and injector are built together, so there is no separate high pressure fuel pipe. Fuel is supplied to the unit injector at low pressure by a transfer pump. Inside the unit injector, a plunger driven by the engine camshaft compresses the fuel to a very high pressure. An electronic control unit or ECU controls the exact time and quantity of fuel injection by operating a solenoid valve. Because the high pressure is generated inside the injector itself, there is almost no pressure loss before injection. This results in finer fuel atomization, more efficient combustion, better fuel economy, and lower exhaust emissions. That is why these systems are widely used in modern heavy duty diesel engines, which are manufactured by companies like Caterpillar, Volvo, MTU, and Cummins engines. The fourth type of fuel injection system is inline fuel injection pump. This is one of the oldest and most widely used mechanical fuel injection system, especially in heavy duty trucks, tractors, construction equipment, and stationary diesel engines. Unlike the individual jerk type fuel pump, where each cylinder has a separate fuel pump mounted on the engine, the inline fuel injection pump uses one common pump housing. Inside this single housing, there are multiple pumping elements with one pumping element for each engine cylinder. For example, a 6-cylinder engine will have 6 plungers and barrels arranged in a straight line inside one pump housing. We can see it here. This straight line arrangement is the reason why it is called an inline fuel injection pump. Each pumping element has a precision plunger and barrel which generate the high pressure required for fuel injection. Inside the pump, there is a common camshaft with multiple cam lobes. As the camshaft rotates, each cam lobe pushes its respective plunger upward. The upward movement of the plunger compresses the fuel trapped inside the barrel. Once the fuel pressure becomes high enough, the delivery valve opens and a high pressure fuel flows through an individual high pressure pipe to the injector of that particular cylinder. After the required quantity of fuel has been delivered, the pressure drops and the delivery valve closes and the fuel injection stops. This process is repeated for every cylinder according to the engine firing order. Now you may wonder how the quantity of fuel is controlled here. In an inline pump, all the plungers are connected to a common fuel rack. When the accelerator is pressed or the governor changes the engine speed, the fuel rack rotates all the plungers simultaneously. This changes the effective pumping stroke of each plunger and controls the amount of fuel delivered to the every cylinder. Since all the pumping elements are housed in one compact assembly and are driven by a single camshaft, the inline fuel injection pump is robust, reliable, and capable of supplying fuel accurately to multiple cylinders. Now let us move to another very important component of the fuel injection system, which is the fuel injector, also known as the injection valve in large diesel engines. The fuel injector is the final component of the fuel injection system. Its job is to inject the correct quantity of fuel at the correct time and at very high pressure into the combustion chamber. But simply injecting fuel is not enough. The injector must also convert the liquid fuel into a very fine spray, and this process is called atomization. The finer the fuel droplets, the better they mix with the compressed air inside the cylinder, and this will result in more efficient combustion, higher engine power, lower fuel consumption, and reduced exhaust emissions. During engine operation, high pressure fuel reaches the injector from the fuel pump or the common rail. When the required pressure is achieved, the injector opens automatically or electronically, depending on its design, and sprays the fuel into the combustion chamber. As soon as the required amount of fuel has been injected, the injector closes immediately, which prevents the fuel leakage and ensures the precise fuel delivery. The common types of fuel injectors used in diesel engines are mechanical injector, electronic injector, common rail injector, and unit injector. Let us understand each of these one by one. Mechanical injector. This is the oldest and simplest type of diesel fuel injector. As the name suggests, a mechanical injector works completely mechanically. It does not require any electronic control. Instead, it operates purely on fuel pressure generated by the fuel injection pump. Inside the injector is a needle valve, which normally remains closed. A spring presses the needle firmly against its seat, preventing fuel from entering the combustion chamber. When the fuel injection pump delivers a high pressure fuel to the injector, the fuel pressure starts increasing inside the injector body. As long as the fuel pressure is lower than the spring force, the needle remains closed. When the fuel pressure becomes greater than the spring force, it pushes the needle upward. As soon as the needle lifts from its seat, fuel passes through the tiny nozzle holes and enters the combustion chamber as a fine atomized spray. The fuel then mixes with the hot compressed air and combustion takes place. Once the fuel pump stops delivering high pressure fuel, the pressure inside the injector quickly drops. and the spring immediately pushes the needle back onto its seat, closing the injector and stopping fuel injection. This entire process happens with a few milliseconds and is repeated during every engine cycle. One of the biggest advantage of the mechanical injector is its simple construction. Since it has no electronic components, it is highly reliable, easy to maintain, and can operate in harsh environments. That is why mechanical injectors are commonly found in large diesel engines, marine engines, power plant generators, agricultural tractors, and other heavy duty industrial applications where reliability and simplicity are more important than advanced electronic control. Electronic injector. As the name suggests, an electronic injector is controlled electronically by the engine control unit or ECU, which is often called the brain of the engine. Unlike the mechanical injector, which opens only when the fuel pressure becomes greater than the spring force, the electronic injector is controlled by electrical signals, which is sent from the ECU. Inside the injector, there is a solenoid valve, or in some advanced engines, a piezo actuator. These components act like electrically operated switches that control the opening and closing of the injector. The ECU continuously receives information from various engine sensors, and these sensors monitor important operating conditions like engine speed, engine load, accelerator position, intake air pressure, coolant temperature, and many other engine parameters. And based on this information, the ECU calculates exactly how much fuel the engine requires at that particular moment. It then sends an electrical signal to the injector. As soon as the injector receives the signal, the solenoid or piezo actuator operates and sprays the fuel into the combustion chamber. The ECU also controls how long the injector remains open. The longer it stays open, the more fuel is injected. As soon as the ECU stops sending the electrical signal, the solenoid is de-energized and the injector needle closes immediately and fuel injection stops. This entire process happens within just a few milliseconds and is repeated for every combustion cycle. The level of precision of electronic injector is much higher than that of a mechanical injector. As a result, electronic injectors provide better fuel economy, improved engine performance, smoother engine operation, easier cold starting, lower exhaust emissions, and better response to changing engine loads. That is why electronic injectors are widely used in modern diesel engines, heavy duty trucks, construction equipment, and many generator sets where high performance and strict emission standards are required. Now let us understand the common rail injector. A common rail injector is a special type of electronic injector that is used in a common rail direct injection or CRDI system. Injector receives fuel from a common rail, which acts like a common high pressure fuel reservoir, which supplies fuel to all the injectors. The engine control unit or ECU continuously monitors the operating condition of the engine through various sensors. And based on engine speed, load, accelerator position, temperature, and several other parameters, the ECU calculates exactly when fuel needs to be injected and how much fuel is required. Since the fuel inside the common rail is already at very high pressure, it immediately flows through the injector nozzle and is sprayed into the combustion chamber as a very fine mist. One of the biggest advantages of the common rail injector is that the injector itself does not have to build up fuel pressure. Its only job is to open and close precisely under ECU control. Common rail injectors are widely used in modern passenger cars, heavy duty trucks, construction equipment, industrial engines, and modern diesel generator sets. Unit injector. As the name suggests, a unit injector combines both the fuel pump and the fuel injector into one single compact unit. Each engine cylinder has one unit injector, which is installed directly in the cylinder head. First, fuel is supplied to the unit injector at low pressure by a transfer or feed pump. Inside the unit injector, there is a plunger which is mechanically operated by the engine camshaft. As the camshaft rotates, the cam pushes the plunger downward. This compresses the fuel inside the injector and generates a very high injection pressure. So unlike a mechanical injector or a common rail injector, the fuel pressure is not generated by a separate high pressure fuel pump. Instead, the pressure is generated inside the unit injector itself. Quantity and timing of injection is controlled by ECU through electronic solenoid. As soon as the ECU cuts off the electrical signal, the solenoid closes the injector immediately, stopping the fuel injection. One of the biggest advantage of the unit injector system is that the fuel pressure is generated inside the injector itself. So there is almost no pressure loss before injection. This results in higher injection pressure, finer fuel atomization, improved combustion, higher engine efficiency, and lower exhaust emissions. That is why unit injectors are widely used in many modern heavy-duty diesel engines manufactured by companies like Caterpillar, Detroit Diesel, Volvo, and MTU. Now let us understand another important component which belongs to engine lubrication system, which is the pre-lubricating oil pump, commonly called the pre-lube pump. As the name suggests, this pump lubricates the engine before the engine starts. It is an auxiliary lube oil pump whose main purpose is to supply the lubricating oil to all critical engine components before the crankshaft begins to rotate. The pre-lube oil pump is generally a gear type or screw type positive displacement pump, and it is normally driven by an electric motor. Now question is, why do we need a separate pump before starting the engine? Actually, what happens when an engine remains stopped for several hours or even days, most of the lubrication oil drains back into the oil sump due to gravity. As a result, important moving parts like main bearings, connecting rod bearings, camshaft bearings, rocker arms, and gear train may not have a sufficient oil film on their surfaces. If the engine is started immediately, these components may experience metal to metal contact for a few seconds until the main lube oil pump builds up the oil pressure. This can lead to unnecessary wear or even component failure. To avoid this, the pre-lube oil pump is started before cranking the engine. The pump draws lube oil from the oil sump and circulates it throughout the lubrication system. It builds up the required oil pressure and forms a protective oil film on all bearings and moving parts. In engine control, there is an interlock between pre-lube oil pump pressure and engine start command. Only after the required lube oil pressure is achieved, the engine is allowed to start. When the main lube oil pump builds up sufficient oil pressure and is able to maintain lubrication on its own, the engine control system automatically switches off the pre-lube oil pump. Next, main lubricating oil pump. This is the one of the most important components of the engine lubrication system. As the name suggests, the main lube oil pump is responsible for supplying lube oil to the engine while it is running. In fact, it is often called the heart of the lubrication system because it continuously circulates lube oil to every critical moving part of the engine. The main lube oil pump starts working as soon as the engine starts running. The pump draws lube oil from the oil sump through the suction line. It then pressurizes the oil and sends it through the oil filter and then oil cooler before distributing it to all important engine components. The pressurized lube oil lubricates the main bearing, conrod bearing, camshaft bearings, rocker arms, gear train, turbocharger bearings, and other moving parts. The main oil pump is generally a gear type or screw type positive displacement pump. It is usually driven by a gear mounted at the free end of the crankshaft. So whenever the crankshaft rotates, the oil pump also rotates automatically. An important feature of the main oil pump is the pressure regulating valve. This valve maintains the lube oil pressure within the required range. If the oil pressure becomes too high, the valve opens automatically and diverts the excess pressure back to the suction side of the pump. This prevents excessive pressure from damaging the oil filter, bearings, seals and lube oil system. Without the main lube oil pump, the engine would lose lubrication within a few seconds, and this would result in excessive friction, overheating, rapid wear of bearings and other moving parts, and could eventually lead to complete engine failure. So in simple words, we can say that main lube oil pump continuously supplies clean pressurized lube oil to every moving component of the engine, ensuring smooth operation, reducing friction, removing heat, and protecting the engine from wear throughout its operation. Now let us understand the HT and LT water pumps, which are important components of the engine cooling system. HT stands for high temperature and LT stands for low temperature. Their main job is to continuously circulate cooling water through different cooling circuits of the engine. As the engine operates, a large amount of heat is produced during combustion. If this heat is not removed, the engine temperature will rise rapidly, which will lead to overheating and possible damage to important components. This is where the HT and LT water pumps play a very important role. HT water pump circulates the cooling water through the hottest parts of the engine, like cylinder liner, cylinder heads, and combustion chamber area. Its job is to remove heat from these engine components and maintain the engine at its normal operating temperature. On the other hand, LT water pump circulates the cooling water through auxiliary components like charge air cooler and lube oil cooler. It helps remove the heat absorbed by these components and keeps the entire cooling system operating efficiently. Both the HT and LT pumps are generally centrifugal pumps. They are usually driven mechanically through a gear mechanism connected to the free end of the engine crankshaft. This means that whenever the engine is running, both pumps also operate continuously. Normally, pump casing, impeller housing and covers are generally manufactured from cast iron because cast iron provides high strength, good durability, excellent casting properties and good resistance to corrosion. And pump shaft is usually made from acid resistant stainless steel. This material is selected because the cooling water contains the treatment chemicals to prevent corrosion and scaling. The acid resistant stainless steel protects the shaft from corrosion and provides a long service life. If we talk about its function, inside the pump is an impeller. As the impeller rotates, it creates centrifugal force that draws cooling water into the pump through the suction side and delivers it under pressure through the discharge side. The cooling water then circulates through the engine, absorbs heat and returns to the cooling system to be cooled before circulating again. And this process continues as long as the engine is running. So in simple words, we can say that the HT and LT water pumps are the heart of the engine cooling system. They continuously circulate cooling water, remove excess heat from the engine and auxiliary equipment, prevent overheating, and maintain the engine at its optimum operating temperature. So with that, we come to the end of today's lesson. If you found this lesson useful, please like, share and subscribe to ProjexCellence ProDigy. Thank you for watching. Namaste, goodbye, Sampai Jumpa.